Now, this is relevant for your compatriot, Sir Roger Penrose, who I'm very fond of. The Nobel Prize was awarded to Sir Roger in October for work he did in the 60s, even before the expression black hole was coined. And in this early work in the 1960s and mid-60s, Penrose writes this paper that is so magical. It's just 3 pages long. And in a paragraph of a mathematical proof, he makes the following argument. He says, imagine, just hypothetically, unhindered collapse of a star. He says, inevitably, the star will curve space-time around it and leave behind, almost as like an archaeological record, the event horizon. It will leave the event horizon behind it. Now, what's the event horizon? The event horizon is a point where the curves in space-time are so strong that light doesn't just bend in an arc. Light cannot escape at all. Every path of light, and therefore everything that travels slower than the speed of light, which is everything, will inevitably continue to fall. So that region is just a point in space-time where to launch a spacecraft that escapes, it would have to travel faster than the speed of light. And since nothing can do that, that region goes dark. Now, the profound thing here is that event horizon is really just a shadow. There is nothing there. And Penrose, in this important paper, goes on to prove that the star can no more hang out, this collapsing star, at the event horizon then it can rush outward at the speed of light, that the star is inevitably forced inward and continues to collapse towards some unknown fate. And we'll discuss its fate in a second. But the important thing I want you to walk away with is the idea that if you were an astronaut and you were in space-time and you were to fall past this region, it would be as undramatic as stepping into the shadow of a tree. And so that's one of these beautiful aspects of black holes that is often misunderstood. Black holes are not dense objects. There's nothing there. The material has long gone. The black hole is a nothingness. It is an empty space-time. And it is more of a place than it is a thing. So as you transit that event horizon, even though you will never make your way out again, because you can't make your way out any more than you can travel faster than the speed of light, you will not actually notice that something spectacular has happened as you cross the event horizon. If I were to give you an accurate portrait of what a black hole looked like, I'd show you something like this. This is pretty accurate. So a black hole alone in the universe is dark because light cannot escape. It is a dark shadow against a dark background. It is technically invisible. And you would not necessarily be alerted to the fact that you had veered hazardously close to a black hole. The way that we detect them, so we didn't begin detecting black holes until the 60s and 70s. The way that we detect black holes is because of the havoc they wreak on their environment. And this painting is from an actual astronomical image where we have, with telescopes, looked at other galaxies out there, entire galaxies, and seen these staggeringly big jets emanating from the galaxies, millions of light years across. That means millions of times the distance light could travel in 1 year, which is very far because light travels very fast. So these jets break out of the entire galaxy. Now, I said that black holes can't let anything out. They trap everything on the inside. So how are these jets forming? They're forming in the debris outside the black hole. It is not material that was once inside the black hole and is thrown out. It's actually churned up from the matter. It's a kind of magnetic storm. It's churned up from the debris that surrounds the black hole. So unprovoked, a black hole is quiet. It is featureless, and it emits no light, and it is completely benign as long as you stay outside. It is not the weapon of mayhem and destruction that's often portrayed to be. But if you instigate it, if you provoke a black hole, it will become the most powerful engine for the brightest beacons we see across the entire universe, like these huge jets emanating from supermassive black holes. So we began to see evidence of this, of smaller black holes cannibalizing companion stars in the 60s and 70s. But it's quite an interesting fact that we had never actually seen a black hole. I mean, after all, what are you seeing if there's nothing there? And it's a point in space and not a physical object. And it wasn't until last year, and I love this, on the centenary of the Eddington Eclipse expedition, 100 years later in 2019, that the Event Horizon Telescope Project returned the first ever human procured image of a black hole. And the reason why this is so hard to take a picture of a black hole, it's not just because what you're really doing is taking a picture of the shadow. So what they really caught was the hot debris around it. I mean, after all, you can't see the shadow of a tree without the sun illuminating it and casting the shadow. You need a source of light besides the tree to cast the shadow of the tree. You need a source of light around the black hole to cast the shadow of the black hole. And that source of light is hot matter and gas that orbits black holes. Now, why is it so hard? Why did it take 100 years to take a picture of a black hole? And the reason is that black holes are heavy, but they are small. And that's the whole gestalt of a black hole. So imagine you took the mass of the sun, as Schwarzschild did when he wrote to Einstein all those years ago, and you crushed it so that it left behind the event horizon and continued to fall inside, leaving this empty shadow behind it. That shadow would only be 6 kilometers across. That would safely fit in almost any city. So black holes are tiny. The sun, by comparison, is 1.5 million kilometers across. So you have this drastic task of collapsing that to less than 6 kilometers before you force the black hole to form. And that's why it was so hard to imagine that nature would allow such a thing. Now, the sun at 1.5 million kilometers across, you could kind of sense of how big it looks on the sky. And it's not that far away. It takes light 8 minutes to get to us. And it's still, it's substantial in the sky. Imagine shrinking that to 6 kilometers at the same location, it disappears. It's way too small to see. Now, the only aspiration Event Horizon Telescope had to observe or take a picture of the shadow of a black hole was to find a really, really big black hole. And they did. They found, we now understand that the center of our galaxy, there's a black hole that is 4 million times the mass of the sun. And it's 26,000 light years away. So at 4 million times the mass of the sun, which is tremendous, it's less than 20 times the width of the sun across. Now imagine visualizing on the sky the sun, imagine taking, let's call it 17, 18 times across, and now push that to 26,000 light years away. And you have the task of taking that picture that is equivalent to resolving a piece of fruit on the moon. And as the director of the project, Shepard Doleman, phrased it, it is equivalent to reading the date on a quarter in San Francisco from New York City. So this was such a bold ambition, and what they had to do was build a telescope the size of the globe. And to do that, they got a bunch of telescopes at different observatories internationally around the world. Again, this beautiful demonstration of science transcending international borders. And they coordinated those telescopes to act as like one giant eye. It was a very sophisticated, ambitious project. It took a very long time. And when they revealed this at the National Press Club in Washington, DC, the big surprise, we all knew what it was going to look like. It was going to look something like this. The big surprise was they had not taken a picture of our black hole in the center of the Milky Way. They had taken a picture of M87, which is a nearby galaxy. It's 55 million light years away, so much further. But its supermassive black hole is 6.5 billion times the mass of the sun. And so that larger black hole at the greater distance was in the sweet spot for them to be able to take the picture. So the first time human beings laid eyes on a black hole for real, directly, was a year ago, which is quite remarkable. Now, I call the book Black Hole Survival Guide, and I give some tips in the book, how to survive a black hole. One of them is obviously don't get too close, but actually, again, you'd be quite comfortable if you were around a black hole. Let's say it's a smaller one, 60 kilometers across, 60 times the mass of the sun. You could safely set up International Space Station or intergalactic space station, interstellar at least, and orbit and watch the fireworks anytime something tried to fall in, and you could safely live out there. What you would be ill-advised to do is to actually try to cross the event horizon. But if you were less attached to this whole concept of survival, you could try it. You could leave your companion Alice back on the space station and decide to go for an adventure in the black hole. And the intriguing thing is, as you got closer and closer to the black hole, the same effect that we just described, that when you're closer to the Earth, your clock runs more slowly than when you're further away, you would find that as you approach this black hole, your clocks looked normal to you, but to Alice, you would appear to be slowing down. Your aging would be slowing down, but to you, Alice, her whole rhythm of things would appear to speed up. All the movies she was playing would be going very quickly. All the music would be at ridiculous speeds, and she would age much more rapidly. And you and Alice, these longtime companions, would find yourself separated by time. Alice would succumb to old age before you ever crossed the event horizon. Her descendants might be there to continue to try to communicate with you, or her clones, or some way of repopulating the space station. But eventually, as you drifted across the event horizon, you would be absolutely forever separated from Alice and her descendants and your space station, which by then would be succumbing to the elements, even in space. And the interesting thing is that even though Alice sees a pure shadow, that the black hole is dark on the outside, for you, the black hole would be bright on the inside, because all the light from the galaxy could fall in behind you. And you would actually have this spectacular view as you cross the event horizon, where eventually the light squeezed like such a tight beam that it would be like the light at the end of the tunnel. You would see this flash of light just as you were pulverized in the center of the black hole. Don't necessarily recommend it. So the extraordinary things to walk away with black holes is that on your trip on the inside, in addition to realizing the black hole is nothing, it is a place, not a thing, that it is bright on the inside if it's dark on the outside. It is also like Doctor Who's TARDIS, in that it is bigger on the inside than it is on the outside. In fact, there's speculation, which is not that popular, to be honest, among physicists right now, but it is an elegant speculation, that as you go to the center of the black hole, you would actually find yourself part of a new Big Bang, as though as you get pulverized by the extreme curvature of space-time and broken down to your fundamental particles and constituents, and as all of those quantum bits find some kind of explosion in the center, you would break out into a new Big Bang, as though your elements were in some kind of cosmic ecosystem. And you would find new expression in a new universe where new stars formed, and maybe sentient life that reflected on such things, and maybe new black holes. So the black hole could be 60 kilometers across on the outside, but as big as a universe on the inside. And in that sense, it's like a TARDIS. Now, I'm conscious of the time, and I want to be able to take Q&A. So I'm only going to vaguely mention that black holes, we know are real. We observe them, we hear them colliding by rippling the shape of space-time like mallets on a drum with the LIGO experiment, which won the Nobel Prize a few years earlier. And yet the collapsed star that we talk about is not synonymous with the black hole. It is just one way nature thought of to make a black hole. In fact, there are other ways you can make a black hole. You can smash things together in a collider experiment. We have never succeeded at doing that, and make a tiny microscopic black hole. The universe may have succeeded in doing that. The universe may have made tiny microscopic black holes in the Big Bang. And so I don't want you to think of a dead star as synonymous with a black hole. It's actually only one way nature thought of to make a black hole. And then we get to this profound theoretical territory of, well, then what is a black hole if it's not a dead star? The black hole is a space-time that is so sharply curved that it has created an event horizon, a region in space-time that is empty, but marks the terrain at which you would have to travel faster than the speed of light to escape. So it marks a certain point in the curvature of space-time. And there are other ways to create such a surreal object. Now, Stephen Hawking, Sir Stephen, became famous for his very subtle realization that when I begin to consider quantum phenomena, black holes begin to do very tricky things. And I'm sorry I don't have time to go into it, but I do spend some time in the book picking apart the quantum aspects of black holes. I mention it only now because it is, in some sense, the most important terrain on which we can do theoretical physics. It is the most important pioneering forefront where we can think about the mathematics that will give us clues to a theory beyond Einstein's, a theory that understands not just curved space-time, but also the microscopic high-energy quantum phenomena. And here is a black hole evaporating, as Hawking predicted. We have never seen a black hole evaporate. We probably never will. But theoretically, it really becomes the terrain in which we begin to explore really fascinating concepts like holography. Is the entire world really just a two-dimensional phenomenon that we have this illusion that appears to be three-dimensional? Are there worlds in a box where an entire three-dimensional universe that we perceive is actually a world in a box and we're under this mistaken illusion? I'm just flirting with these ideas here. I'm not actually trying to explain them. Are there quantum wormholes that entangle the interior of a black hole to the exterior? So we get from this theory of Einstein's in 1919, this mathematical discovery, nuclear physics driving the realization that nature is going to make black holes, has found a way, the discovery of actual black holes in the universe, to bringing us to the shore of this very theoretical reality where black holes loom very, very large. So thank you very much for joining me and your attention, and I'd be honored to take questions where I think I need help from our moderator.